Hello, I'm going to talk to you about clay formation and process. Before I get started, I just want to send a special thanks to Steve Laux for some information that I got from him off the internet, and Margaret Keelan, who gave me the first draft of this presentation, which I have subsequently adjusted throughout the years. So, what is clay and how is it formed? Clay is the product of natural forces working of the face of the earth over millions of years. Simply put, clay is weathered rock. Agents of this weathering are wind, water, and glaciers, which act upon rock, causing it to disintegrate and often travel, mixing with other chemicals and impurities to finally settle out in quiet waters. So clay is rock, tiny particles of rock. Wind blowing on the surface of mountains, tearing off crumbling little pieces of rock that tumble down. Glaciers tearing through valleys, ripping bits of rock off of the walls and tumbling them, smashing them, grinding them. And then finally, rivers. Glaciers melt, rivers flow, they continue to tumble and carry these particles. Now, these are the clay cliffs of Omarama in New Zealand. Not sure if I'm saying that right, but all over the world, you're going to find ancient clay deposits where once there were rivers that carried these particles to a specific spot. And because of the size and the density of those particles, the similar size and density, they move together and they settle in specific spots. Here in California, in the Central Valley, much of it was once floodplain, and that's why you find some great clay deposits out here. So a secondary clay, this is a ball clay deposit in England that's being mined. And so secondary clay, it's found away from its point of origin. It has traveled a long way. It's a secondary clay. A primary clay is more rare, and it's found in the spot where it's formed. Here is a primary clay, a kaolin deposit. It's usually kaolin. This is in Venezuela, and water percolates through rocks, causing them to break down, causing chemical reactions. And that's how you get the primary clay. Primary, it's found in the spot where it's formed. What is that stuff we get in a bag when we go to the clay store? It is a clay body, which is a specially formulated combination of clays and materials to serve a specific function. So this might be the most common, a stoneware. Usually fires to a higher temperature. It has grog in it. It's usually going to have a buff sort of color. This over here is probably a terracotta, which is a low fire, high iron earthenware meant to be fired at a low temperature to be very porous, usually for planters and such. And then this might be a smooth, high fire throwing clay. Maybe high iron content, manganese content, something that's making it dark and brown. And then this one is most likely a porcelain, a pure, mostly kaolin clay that's going to be a mostly primary clay, not going to have grog in it. It's going to have a beautiful white color when it's fired. Glazes are going to look real nice on it, but it's going to be a pain to deal with because it's going to feel like butter because it has no body to it. So what is in a clay body? Well, clay, most likely. The majority of the clay body is made of clay, which is made of finely ground minerals that are refractory or heat resistant. Flux or frit is a glass formulated to melt at a specific temperature, which helps the clay body mature or vitrify at a specific temperature. So frit is a formulated, specially formulated glass, and it's a type of flux. But there's other naturally occurring materials that you can use as a flux. So frit is a flux. Frit is the man-made version. Grog is fired and ground bits of clay that can help the clay hold shape when wet, shrink less during firing, and withstand more thermal shock. Thermal shock being changes in temperature. So imagine if those little bits of clay, when you fire clay, it shrinks. When clay dries, the moisture leaves it, and that space between the clay becomes smaller because there was water there that got smaller. And then as those particles begin to melt, they get closer together and the clay shrinks. So if that clay's already been fired, like the grog, it's not going to shrink, and it's going to give the clay, make it shrink less, so less stress, less thermal shock in the firing, and also it's going to give it some body while you're building with it or throwing your pot. It's going to stand up and not be all squishy and fall over. So porcelain, primary clay, mostly kaolin. A stoneware usually is going to be high fire. Porcelain is usually high fire. There's mid-range porcelains. So stoneware, it's going to be a secondary clay. It's going to have more impurities in it. And those impurities are not a bad thing. They can give it some interesting color. They usually give it more elasticity because of the variety of particle sizes. It's going to be more kind of stretchy. It's going to be less crumbly. It might have some kind of speckling in it, like this clay here, and that is from usually iron or manganese, which causes the speckling. An earthenware refers to any low fire clay, and terracotta being one of the most common types of earthenware, and that has high iron content, which makes it red or brown. And it's meant to be fired to a low temperature. It can only be fired to a low temperature, but usually it's under fired, so it's kind of porous. And I just want to show you here how clays can really change color when they're fired. So here's a red earthenware when it's wet, and then when it's fired, it turns more red. Look at this earthenware. This one has a lot of talc nowadays, has kind of a darker grayer color, and when it's fired, there's a lot of earthenwares, low fire clays have a lot of talc in them. So then, but it fires white. So just remember the color of the clay wet and the color of a glaze, the color of a slip, all those things, underglaze even, they change when they're fired. And depending on the specific temperature that you fire it to, the color can really change. So here is a brown clay, and then fired to cone 04, cone 4, cone 5, cone 6. This is increasingly hotter and hotter and hotter. It loses its color saturation. And then also you can see here porosity, so how porous it is, how absorbent is it. It's going to be increasingly less porous as you fire it hotter, as it gets closer and closer to being vitrified. And then it's going to shrink. The shrinkage rate goes up because it's shrinking. Now, what happens when it becomes solid? Well, if you can imagine, as I mentioned before, all those particles of clay have water in between them. Here are the particles. As the water leaves, the particles get closer together. Shrinking begins to happen. When it's bone dry, it's going to be absorbent because of the spaces between the particles. It will absorb moisture. So you fire it to a lower temperature, and imagine these particles as beach balls, and as they squish together, here's like the flat spot that would happen if you squished two beach balls together. It would have a flat spot, right? But there's still going to be some space in there. So your bisqueware is going to be kind of like this. The particles are sticking together, but there's still little gaps in between the particles which can soak up glaze, which makes it absorbent, right? So you dip it in your glaze, you paint your glaze on, that thirsty clay absorbs that material. Then, as it gets hotter and hotter, the beach balls squish into each other more and more. The particles squish into each other until there's less and less, and finally no space. No space. And that's called sintering as they squish together. So imagine if you took a huge container of beach balls and you put it under pressure. At some point, assuming they didn't pop, they would all stick together and there'd be no space in between them. And that's what you get when something is vitrified. Vitrified, which relates to the word vidrio in Spanish, which means glass, vitrified. So those particles, once they're at their maximum density, they are the most strong. They are very strong. They are no longer porous or absorbent. And if you heat them up beyond that point, they're gonna melt. And so it's kind of nice when something is vitrified because it starts to melt just a little bit, especially porcelain. It gets a really beautiful kind of glossy finish to it. But if you go beyond that melting point, it will become a liquid glass. So that's why there's clays that fire to different temperatures, and you have to fire them to the correct temperature and not overfire them. This is a chart, cone chart. So a cone is literally a piece of clay that is designed to melt at a specific temperature, and each cone will have a number on them. And the numbers start around 022, and they will count down as the temperature gets hotter. This is the ultra low range here. Not much happens in that area except for like decals and lusters are going to happen around 018. So the numbers count down until they get to 01, and then they start counting back up again. So they count down, 01, and then cone 1, and they start going back up. I think of that sort of like BC and AD that happens right here, right? Time is measured it counts down and then counts back up in terms of how we count it. And so these numbers refer to a specific temperature, so it's a lot easier to say cone 4 than it is to say 2,167 degrees. So that's why we have that system. Low fire, this is going to be more like the sculptural type of work where it's usually might be less vitrified. You're going to get more vibrant colors, less stress on the materials. So that's more of like a sculptural range. And then it's low fire. Low fire is the blue. Mid fire, mid range. Then you're going to go to this can be sculptural or pottery, but it's mid-range. High fire is going to be more for pottery, and you can fire a sculpture at a high fire temperature. You can fire pottery at a low fire temperature, but low fire pottery is going to be more fragile. So a high fire clay fired to its maturity, to its vitrification, is going to be the strongest thing. A high fire clay fired to a low temperature is going to be more porous, less vitrified, less strong. A low fire clay fired to a low fire temperature is going to be pretty strong, but not strong enough for functionality. I mean, it'll function, it'll work, but it's not going to be the best. Cones. So yeah, we talked about what they are specifically, and so they have little numbers on them which refer to the temperature that they're fired to. This is a cone pack, and so you're going to have cones in a cone pack in usually a gas kiln or in a raku kiln maybe, or a wood fire kiln. But so say you have right here, say you have cone 5, cone 7, and cone 9. And so you can see the temperature probably on the top and the bottom of the kiln. You're going to have cone packs. You can see, okay, 5 is down, 7 is at 10 o'clock. So then you can really measure that temperature very accurately. more accurately actually than thermometer, because the clay doesn't lie. In old school electric kilns are going to have a cone sitter, and the cone will sit on there. When the cone melts, this bar falls. The cone is supporting this bar. When it falls, turns off the kiln. So that's old school electric kiln. Electric kiln, yeah, this is an electric kiln here. This is a new school one. We'll get there in a sec. So high fire usually is going to happen in a gas kiln, but you could do it in electric. But what the gas does generally is heats up the kiln more efficiently than electricity will, or it's better for heating up the kiln than electricity. And you have that element of gas. And what you can do with gas is you can affect the atmosphere. And most often, you're going to want to create a reduction firing, meaning you reduce the amount of oxygen in the kiln. A regular efficient firing is called an oxidation, where you have a more equal level of oxygen. But in a reduction, you use the gas to starve the glazes of oxygen. And what that does is it brings out more vibrant colors. It can make the iron in the clay come out a little bit more, and you get some more kind of that beautiful magic that you associate with high fire pottery, versus an oxidation, which is going to be not as exciting. And so the way that you reduce the oxygen and increase the gas is you can turn the blowers off on when you're letting the gas into the kiln on the burners. You can turn the blowers off. Usually there's a damper on the top of the kiln. Sometimes there's one on the bottom. And you can close off the damper to allow less oxygen to escape and kind of choke out the kiln that way. And then you can also just turn up the gas. So here you can see the burners, and usually there's a little fan right here, so you can turn up the gas, turn the fan down to create that reduction, and that can usually happens towards the end of the firing. Though you can do your body reduction during the firing, but there's details to that we don't need to get into. So what does that look like when you do that reduction? Well, here is a glaze, and when you dip your piece into the glaze, it's usually this kind of opaque type of consistency. And so this glaze, it's got a lot of copper in it, so that's what makes it green. Now copper, when you starve it of oxygen, it often turns red. So here it is heavily reduced, this glaze. Here it is with less of a reduction. Some of that copper remains green, some of it's red. Less reduction here. And then finally oxidation. It looks totally different. So the copper remains green in that oxidation. So here's the difference of what you can get with the same glaze in a reduction versus an oxidation. High fire. Though you can do reduction at lower temperatures, but that's less common. Low fire and mid-range usually is a oxidation firing, which happens in an electric kiln. And this kilns, I think of them usually as a microwave combined with a toaster. So the microwave would be the outside right here, where you can program in a ramp. You program in a set of segments here, and what you're telling the computer is, okay, how fast do you want me to heat up? What temperature do you want me to get to? How long do you want me to stay at that temperature? And so the computer communicates with a little thermometer inside of the electric kiln called a thermocouple, and that takes the temperature, and the computer makes decisions based on the program and the feedback that it gets from the thermocouple. And the decisions that it makes are how much electricity to put through the element. So the element is the toaster part, just like your toaster at home. It is a wire made of usually canthal or nichrome, and it conducts electricity inefficiently, and because it is inefficient at conducting electricity, it releases heat. And usually don't do the high fire firings in the electric kiln. You can, but you usually don't because it can wear out the element pretty quick. And so it's just hard on your kiln, and you can't get the reduction unless you like light something on fire inside your kiln, which is untraditional and also not good for your kiln. What do we use for decorating? Well, there's a lot of things. We can use glaze. We talked a little bit about that, but the most predictable material that you can use are underglazes or slips, and basically that's a liquid clay with a mineral pigment in it. So a slip or an ungobe are usually a more simple, just kind of like clay, water, maybe a deflocculant, and the mineral pigments. Versus the underglazes are going to be a little bit more engineered to have more predictable and versatile results. Slips quite often can only go on leather hard clay. We'll talk about what that is. There's different stages of clay. Sometimes they can go on Bisqueware, but usually a slip or an ungobe go on leather hard clay. And there's a lot of wiggle room on like what you call an ungobe and what you call a slip, so I won't get into that. But underglazes usually can go on at any stage. They can go on greenware, they can go on like wet greenware, leather hard, bone dry, they can go on bisqueware, so they can go on any stage. Let's talk about the stages of clay first here. So unfired clay is called greenware. It's green, it's young, it's new, it's old, it's rock, but it's new to you. Bisqueware, it's been fired once at a lower temperature and it's going to be porous. We talked about that. And that name comes from England, where they looked at the clay, they fired it once, and they're like, that looks like a biscuit. So they would call it Bisqueware. So that's how you can remember it. Glazeware, it's fired clay with glaze on it. It's vitrified, usually pretty vitrified. Not necessarily 100%, but it's going to be more vitrified. So those are the stages of clay: greenware, bisqueware, glazeware. And within greenware are different phases. The wettest phase being slip, which can be used for attaching things, for decoration. There's a lot of different ways of kind of engineering your slip, or slip casting, which is a whole thing unto itself. Wet or plastic clay, that's when it comes out of the bag. It's plastic, meaning like movable, manipulatable. And then comes leather hard, where it's starting to get stiff, but it's going to hold its shape much more. This is good time for slab construction, for beginning to add more detail. And then finally, bone dry. That's when it's ready to go into the kiln. You can't really manipulate it other than carving or sanding it, and it is no longer cool to the touch. It's changed color. That's bone dry. So those are the stages of greenware, unfired clay. And I want to go back here, and oh my goodness, what happened to this poor rabbit? Well, let's do a forensic analysis. So why did it blow up? Well, there are several reasons. It appears that it was too thick here. Usually when you build thicker than 1 inch, the moisture inside of the clay cannot escape. And if you heat your clay up above the boiling point, 212 degrees Fahrenheit, the liquid inside of the clay, the water that's still in there, will become a gas, and it will expand, and it will escape. And if it cannot escape, it will find its own way out by exploding your sculpture. So that's why things that are thicker than 1 inch usually dry too slow for us, for our firing. So we try to always keep things thinner than 1 inch. And that's why we also will hold, if we're doing sculptural stuff, we're firing it, we do that bisque firing slow, and we will hold it at around 200 degrees for say at least 5 hours, to give that moisture a chance to escape. Also, air expands when it heats up, and if the air is trapped, like as in if there's no hole anywhere, it can be as small as a pinhole, but if there's no hole in this body anywhere, then the air cannot escape, and when it heats up, it expands and it will find a way out. So you got to give it a way out. And air bubbles can be created not only by like creating the sphere, maybe with 2 pinch pots, but also if you do a bad attachment, like here, maybe they didn't score enough, or the clay wasn't wet enough when they attached it, but an air bubble got created here when they added clay over clay. It created an air bubble, it expanded, it exploded. So, lessons to learn: don't fire your clay too fast, don't build thicker than an inch, make good attachments, and always put a hole somewhere, even if it's as small as just stabbing it with a needle tool. So Bisqueware, we know about that. Glazeware. So yeah, the stages of clay are greenware, Bisqueware, Glazeware. And then there are several stages of greenware. Glaze. What is a glaze? Well, generally, it's going to have these 3 things in it: flux or frit, refractory / alumina / clay, silica, which is the glass former, because it's mostly going to be glass. We're melting glass over the surface of our sculptures and pots. So a flux controls and brings down the melting temperature, causes the glaze ingredients to melt together. So lots of different materials can be used as a flux, and those materials have specific characteristics such as opacity and color. There's also a frit, which is a man-made material designed to melt at a specific temperature that is often used as a flux. So a frit can be used as a flux. It is in both clay and it is in glaze. The refractory, or alumina or clay. So basically think of it as, I know this is too many words, but people will call it these 3 different things. Basically, it is clay. Usually it is alumina, specific type of clay, and it's used as a refractory. So refractory means that it can handle heat, can handle thermal shock, and stands up to heat. Many clays are made up of mostly alumina. It controls the viscosity, so it controls how much that glaze will flow, right? So if your glaze is running off of your pot, I need more alumina to keep that glaze from running off of the pot. It raises the melting temperature. So, my glaze, not only is it running, it's too flowy, it's flowing too much, but also it's melting really quick. So those are kind of like almost the same problem, but there's some slight differences. Helps the glaze stick to the surface. Yeah, so that's what it can do. It can also control opacity, can make things a little bit more opaque. Silica is the glass former. It raises the melting temperature and creates a glossy surface. Usually it is made of quartz. A feldspar. So that was not mentioned. This is not mentioned here, but in reality, a glaze is usually, you start with a feldspar and you use these materials to adjust its characteristics, because a feldspar has characteristics of these 3 materials. So this is what feldspar, naturally occurring material that contains all 3 ingredients. So this is what a glaze recipe usually looks like. It's going to have a feldspar, and then you have your flux, your clay or refractory, your silica, glass former, and together these 4 ingredients are going to add up to 100%. Remember, the feldspar has aspects of these 3 things. So you're adjusting the feldspar using these. Together they add up to 100%, and then you add the colorant, whether that is a mason stain or an oxide or something like that. So when you see a glaze formula, you're like, hey, but this adds up and there's no color in it. That's just how it works. Because you can do stuff with the colorants. You can change them if you want. Well, you can change your glaze as well, but that gets a little more risky. So yeah, here is a glaze formula, and this has a high silica content, which is going to make it more glossy. The end. Hope you've enjoyed this presentation.